Just have a short look at page 12 of your worksheet. This is November 2016 P41. Okay. The first part of your question is actually related to ideal gas. I haven't taught you ideal gas, but I think you guys would have gone through this in your chemistry if you're taking chemistry. So in your current question here, you have an ideal gas that is initially at a pressure of 1 times 10 power 5 Pascal, volume of 4 times 10 power minus 4 meter cube, and a temperature of 300 Kelvin as illustrated in the figure below. A change in energy of the gas of 240 joules results in an increase in pressure to a final value of 5 times 10 power 5 at constant volume. The thermodynamic temperature becomes T. Calculate out the temperature T here. Okay, so you're going from this initial state to this final state. Okay, and what relates both of them together is the ideal gas equation, PV equals to nRT. Okay, the question has already mentioned that this is an ideal gas here. Okay, so if you compare between the initial and final state, the equation that links both of them is PV equals to nRT. What is actually constant between both states is that you have constant volume, you have the same number of moles because this one is considered as a closed system. You did not actually add or remove any of the gases. So your number of moles N here is the same. And then your molar gas constant is also assumed to be, your molar gas constant is also a constant. Okay. So PV equals to nRT, V, N, and R are constant. Therefore, pressure is proportional to temperature. So you want to find the final temperature T here, which is actually your T2. You will just say T2 to T1 equals to P2 to P1, such that T2 is P2 to P1 times T. You already know your pressures. This one is 5 times 10 power 5. This is 1 times 10 power 5. And this is the temperature for the first state, T1. So you sum everything in, you get your final temperature is the 1500 Kelvin. Okay. So this is pretty straightforward. And then the next part requires you to find out your amount of gas. Okay, you can just use PV equals to nRT again, either applied to the initial state or the final state. It doesn't matter which one you apply it to because your number of moles is actually the same for both cases. So say I apply for the first case, the initial state, I will say P1 V1 equals to nRT1. I sum in the values for pressure, volume equals to number of moles times molar gas constant 8.31 times your thermodynamic temperature. You will get your number of moles as 0.016. Okay, so this one is applied for the initial state. If you apply PV equals to nRT for the final state, you also get back the same answer. Okay, so it doesn't matter which one you use. Okay, so this one is just some basic calculations related to ideal gas. The next question is the one that is directly related to what you've just learned. Now, here, they mentioned to you that the increase in internal energy delta U of a system may be represented by the expression delta U equals to Q plus W. State what is meant by these following symbols. If you have positive Q, as I mentioned, it's actually heat energy or thermal energy supplied to system. If you have positive W, it's actually work done on system. Okay, following what you see here from thermodynamic first law. The positive, negative each have a specific meaning. Okay, so that's what you're trying to do here. Okay, positive Q, positive W, use their respective meaning. Thermal energy supplied to system, work done on system. Okay, now then for question part 2, they want you to calculate something out. Find out what is delta U, what is positive Q, and positive W. Okay. So what can you say here now is this. Now, when they told you that there's a change in energy of the gas of 240 joules that results in an increase in pressure, this change in energy of your gas is actually referring to an increase in internal energy of 240 joules. Now, how do I know it's actually an increase in internal energy rather than a decrease? It's because you can see that your pressure has increased. See, your pressure has increased, and also not to mention your temperature has also increased. You are finding what's the second temperature just now, isn't it? The temperature of the final state here. This one was 1500 Kelvin. So here, you notice you're going from 300 Kelvin to 1500 Kelvin. Your pressure was also going from 1 times 10 power 5 to 5 times 10 power 5. You have increase in pressure, you have increase in temperature. Therefore, your internal energy must be increasing. Okay. So here, I know that the 240 joules is actually referring to an increase in internal energy. So the value is actually positive here. Okay, so let me just erase all whatever you have here. So I know that delta U here is an increase in internal energy. It's actually going to be positive 240 joules. Okay, you can just omit the positive if you want to. Okay, as I mentioned just now to you, if you don't write any sign there, it's already automatically assumed to be positive. Okay, so this one is your increase in internal energy. How about your positive Q and your positive W? Now, if you refer back to the thermodynamic first law of thermodynamics, it was mentioned that increase in internal energy is equals to the work done on system plus heat supplied to your system. Now, one thing to note earlier just now was that they told you that going from state 1 to state 2, you had constant volume. When you have constant volume, you have no work done. Therefore, your delta W is 0. So that will explain to you why this one is 0 here. And then after that, if you now look at your thermodynamic first law, which is this one, if your internal energy is plus 240, and then your work done is 0, your delta Q must therefore be 240, positive 242. So it's actually heat supplied to system. So this one here, the answer is 240. Okay. So this is just a simple application of your thermodynamic first law. Okay. Now then after that, we go on to a separate question. This one should be page 24 now. Okay, so just have a look at page 24. It's the start of your question is actually on page 23. Sorry. Okay, so I think you move on to page 23 first. This is November 18 P41. So for this particular question, you are asked to define what is meant by the internal energy of a system. Internal energy of a system was already defined for you inside your notes. You just take the definition from your notes where you say it's the sum of a random distribution of kinetic and potential energies of molecules inside a system. Okay, it's worth 2 marks. Where did the 2 marks come from? If you say sum of kinetic and potential energies of molecules in the system, this is 1 mark. If you say it's a sum of a random distribution of kinetic and potential energies of molecules in the system, the word random distribution here, specifically random, gives you another mark. Okay, so this is a keyword here. Because the idea here is that your molecular KE and PE, they all have different values. If you want to get your internal energy, you need to sum up all those values. Okay. Then you move on to B. You have an ideal gas that undergoes a cycle of changes as shown in the figure below. At point P, the gas has volume 950 centimeter cube, pressure 2.1 times 10 power 5 Pascal, and temperature 280 Kelvin. The gas is heated at constant volume and 97 joules of thermal energy is transferred to the gas. its pressure and temperature change so that the gas is now at point Q. The gas then undergoes the change from Q to R, and then from R back to P. Okay, so there are certain things here that you can actually try to identify first. The first part is where they told you in the second statement in orange here, your gas is heated at constant volume. When your gas is heated at constant volume, there's no volume change here. Volume change is 0. Therefore, work done is 0. And then after that, they also mentioned to you that 97 joules of thermal energy is transferred to the gas. This one is actually telling you that your heat is positive 97 joules. You are actually having heat supplied to the system rather than having heat released from the system. Okay, so you are going from P to Q to R, then to P. You're going across one whole cycle like this, according to what the question has said to you. Now, if you move on to the subsequent part, you don't need to do the table first because they didn't ask you to do that yet. You just look at part 1. They want you to state the total change in internal energy of the gas during the complete cycle PQRP and then explain your answer. Okay, so if you recall how the graph looked like, it actually looks something like this. It's almost like a triangle. Okay, is it? Yeah, it's almost like a triangle there. Okay, so you are going from cycles, you're going across one full complete cycle from P to Q to R back to P. Okay, so let's consider this. Internal energy, as I mentioned to you, is the sum of your KE and potential energy of your molecules. But if you recall that the question mentioned that this is an ideal gas, they already mentioned that in the first part of your question, it's an ideal gas. Ideal gas has no intermolecular force. This one I read it as short form IMF. Therefore, PE is 0. Okay, ideal gas has no intermolecular force. Therefore, PE is 0. So internal energy of ideal gas is therefore just your kinetic energy of your gas molecules. Okay. And then one thing to also note is that I mentioned to you that kinetic energy of your gas molecules is 3 over 2 kT, which means that KE is proportional to T. Okay. If you now look at this equation, I think I better just write it as equation 1 and equation 2. If I relate 1 and 2, I will get internal energy is proportional to temperature, such that any change in internal energy must be proportional to the change in temperature. Okay, this is one relation that you will tend to use quite a lot. Internal energy change is actually proportional to your temperature change for an ideal gas. Okay, it comes from these two equations that you see above. First, the part you say that internal energy is equal to the K of your gas molecules only. And then second comes the part where you say that kinetic energy is proportional to temperature. If you combine both of them, you're going to get IE proportional to T, which subsequently means that change in internal energy is proportional to change in temperature. Okay, so let's just consider this now. When your gas went through a whole complete cycle from P to Q to R back to P, what is your temperature change? Your temperature change ought to be 0, isn't it? Because if you just look at your original graph, P was at 280 Kelvin, Q is at 372 Kelvin, and then R was at 332 Kelvin. Okay, so when you went through a full cycle from P to Q, and then Q to R, and then R to P, you started off at 280 Kelvin, and then you went back to the same 280 Kelvin after one complete cycle. So what you could say here is that for one complete cycle, your temperature change is 0. Therefore, your change in internal energy should be 0. Okay? If you look at your answer that's written here, it's actually telling you that. Okay? The final temperature of the final temperature after going through one cycle is actually equal to your initial temperature. There's actually no change in your KE. Since internal energy of ideal gas consists of only KE, there's no change in internal energy. Or this one is explained using a different manner. I did not combine them. Okay, this one I think is explained using a different way. I will show you how this one is explained. This one is basically saying that KE is proportional to T. If your temperature change is 0, your KE change is 0. And then your internal energy is equals to KE only for ideal gas. Since your KE change is 0, your internal energy change is 0. Okay, this is according to what your written answer here is explaining. Because you say that your final temperature is equals to initial temperature, there's no change in your KE. That one is referring to point number 1 here. And then after that, you have to relate to the part that internal energy of ideal gas is only KE. So since there's no KE change, your IE change is also 0. Okay, it can also be explained like this if you had wanted to. But the way I explained it initially was that I combined all the relations together. You could have also explained it this way if you had wanted to. Okay, so either one works just as fine. All right. Now, if you move on to part 2, part 2 is where you need to complete the table of the energy changes. You have to look at your table column by column. Okay. So here you notice that for the changes from P to Q, Q to R, and R to P, the quantities that are listed would be thermal energy transfer to gas, work done on gas, as well as increase in internal energy of the gas. So all these three quantities actually relate to one equation that you've just learned just now. That one is your thermodynamic first law. Okay, your thermodynamic first law is delta U equals to delta Q plus delta W. Okay, so let's just consider for the first change from P to Q, the first column itself. If you look at the change for the first column from P to Q, which is really this line here, okay, this one, if you recall, it was a pressure volume graph. Okay, this one was a pressure volume graph. If you went from P to Q, it was a straight vertical line, meaning to say that you have no change in volume, isn't it? Okay, if you're going from P all the way to Q here, you have an increase in pressure, but you have no changes in volume because it's still a straight vertical line like this. So in your case, you could actually say that there is no change in volume, so your work done is 0. So this part here, work done is 0. And then after that, you apply your thermodynamic first law. If you already know that your internal energy was positive 97, your work done is 0. Your delta Q by right should be positive 97 too. so that your equation balances. So here, your increase in internal energy is actually just positive 97. Okay, or you can write it in the proper equation form like this. Now delta U is delta Q plus delta W. Your delta Q is 97, your delta W is 0, so you get this. Just like explain it the other way around, didn't I? Sorry. I say increase in internal energy is 97, right? This one, thermal energy transfer to gas is plus 97. Work done is 0. So at the end of the day, your increase in internal energy must be plus 97 so that the equation balances. Okay? So it's actually the same thing, all right? You can either do it this way or you can either do it this way. It doesn't matter which one you use. Okay, so that was for the first column. Then you go on to the second column. For changes from Q to R, this one is your second column here. They already told you that your thermal energy transfer to the gas is 0. Your work done on the gas is negative 42.5. What is then your increase in internal energy of your gas? So what you could do is you can probably just look at this one and try and put in certain values there. Your thermal energy transfer to gas is 0. Your work done on gas is negative 42.5. So that leaves your internal energy as negative 42.52 in order for the equation to balance. So it must be this one. Or you can write it in equation form like this properly. Delta U is delta Q plus delta W. Delta Q is 0, delta W is negative 42.5. So delta U is negative 42.5. It's also the same thing. It doesn't matter. Okay. Now then, if you move on to the last column here, from changes or from R to P, they only give you the work done on gas as plus 37 joules. And then they did not give you the values for thermal energy transfer to the gas as well as increase in internal energy of the gas. The previous two, you had two complete values and just one missing value. But this current one, you have two missing values and just one complete value there. So this one is a bit complicated. You have to make use of what you have actually explained here in part 1. Now, in part 1, you say that as your object went through one full complete cycle, the change in internal energy is 0 because the temperature change is 0. So let's consider this. If you have gone through one full complete cycle, the change in your internal energy for that whole complete cycle will consist of the change in internal energy from P to Q plus change in internal energy from Q to R plus the change in internal energy from R to P. This one will have been the internal energy change for the whole cycle. Okay, it's just that in your current case, because this is a closed cycle, you start and end at the same point, this entire thing should equate to 0. Okay, so now if you look at your working here, change in internal energy of your whole cycle is 0. So it consists of change in internal energy of P to Q plus Q to R plus R to P, which equates to 0. Now, when it comes to the change in internal energy for each of the processes, you actually have the values for two of them. You know from P to Q is 97, Q to R is 0. Sorry, sorry, I read the wrong row, sorry. I keep thinking that the first row is internal energy. I'm supposed to read the last row, sorry. So from P to Q, you know that the internal energy is plus 97. From Q to R is negative 42.5. So you put it inside your equation now, positive 97, negative 42.5, you will be able to find out what is the internal energy change of R to P, which was the missing value here just now. So internal energy change of R to P is negative 54.5 joules. So this is how you get the first value in that column. And then after that, now you have these two values, you can now work out what is the last one by applying thermodynamic first law. So if you know that your increase in internal energy here is negative 54.5 and your work done on gas is plus 37, you'll be able to work out the heat supply as negative 91.5 joules in order for the equation to balance. Now, in your current case, doing it like this may not be the easiest way. It'll probably be easier to look at it like this. Delta U is equals to delta Q plus delta W. Delta U was negative 54.5. Delta W was positive 37. Find out what is delta Q. Delta Q is negative 91.5 joules. Okay, so this one is your last value. Okay, so that is for that specific part. Let's have a look at page 20 of your worksheet. This one is question 3, June 2018, P41. So here, you have state what is meant by internal energy of a system. This one, you just copy the definition from your notes. It's the sum of a random distribution of kinetic and potential energies of molecules in a system. So this one is a pretty standard definition that always will come out. Now, in part 2, explain why is it that for an ideal gas, the change in internal energy is directly proportional to the change in thermodynamic temperature of the gas. Now, this one is actually related to that explanation that I actually wrote for you earlier for the first or second question. So the first thing was internal energy equals to KE plus PE. Ideal gas has no intermolecular force, therefore PE is 0. So this gives you the conclusion that internal energy is equals to KE. And then after that, mean KE is proportional to temperature. This one you will learn further in your ideal gas chapter. The original equation was 3 over 2 kT, such that you can say that mean KE is proportional to T. So these two equations here, IE is equals to KE and KE is proportional to T. Maybe I don't put the mean here. I just write KE is 3 over 2 kT. If you try to equate these two, 1 and 2, you compare 1 and 2, you will get internal energy is proportional to T, such that change in internal energy is proportional to change in temperature. Okay, so this is what you are supposed to get. This one, you could say that KE is 3 over 2 kT, so K is proportional to T. Okay, so this is the actual derivation of the equations. Now you have to put it into words. So when you put it into words, it looks like this in your answer. You say ideal gas has no intermolecular force, so has no potential energy. Therefore, internal energy of ideal gas is solely your kinetic energy of your particles. And then next you say that mean kinetic energy of particles is directly proportional to thermodynamic temperature of your gas. Thus, internal energy is directly proportional to thermodynamic temperature of your gas. That's why here you would say that change in internal energy is directly proportional to change in thermodynamic temperature of your gas. Okay, so that is for this particular question. Then I move on to a separate question. So have a look at page 16 of your worksheet. But the beginning of the question is page 15. All right, so have a look at page 15 actually. That's the beginning of your question. So you look at page 15, this is March 2017 P42. So this question mentions that the first law of thermodynamics can be represented by this expression, delta U is equals to Q plus W. State what is meant by the symbols in the expression. We've done something similar before this. If you have positive delta U is increase in internal energy. If you have positive Q is heat energy transferred to the system, supplied to the system if you want to. And then the positive W is work done on system. Okay, it's a pretty standard term that it will often be tested on. Now, if you look at B, you have a fixed mass of ideal gas that undergoes cycles ABCA of changes as shown in this figure here. During the change from A to B, the energy supplied to the gas by heating is 442 joules. Use the first law of thermodynamics to show that the internal energy of the gas increases by 265 joules. Now, you are supposed to consider only changes from A to B. Okay, only consider changes from A to B. For changes from A to B, they've already told you that the energy supplied to the gas by heating is 442 joules. So this one already tells you is positive delta Q because heat is supplied to system. Okay, and it's worth 442 joules. From there, you're supposed to use the first law of thermodynamics to show that your internal energy of your gas actually increases by 265 joules. So you need to find out the work done first, because when you're talking about first law of thermodynamics, delta U is delta Q plus delta W. You already know that your heat supply is plus 442. You want to show that your internal energy increases by plus 265. You need to first find out what is your work done in order to prove this value here. So now if you're talking about from changes from A to B, is this horizontal line here? What can you say about from A to B here? If you look at changes from A to B, notice that this is a pressure volume graph. From A to B, this one is constant pressure. Okay. And then after that, you will also notice that going from here to here, your volume increases. So this one, you will see is constant pressure. And this one is volume increase. So when volume increase, work is done by system. Okay, work is done by system now. Therefore, your delta W is negative. Therefore, you get negative delta W. Okay. So constant pressure case here would tell you that your work done is actually your pressure times change in volume. Okay, so this is actually fact number one. I'll say this is constant pressure. If you want to find your work done, your delta W is actually pressure times change in volume, which in your case is 5.2 times 10 power 5 as the pressure, and then your volume is 5.0 minus 1.6 times with 10 power minus 4, giving you a value of 176.8 joules. Okay, but because you have volume increase, which means work is done by system, your delta W here is supposed to be negative. Okay, so this one here will be delta W is negative 176.8 joules. Okay, so if this one you sub it in as negative 176.8, you add these two up, you should be getting this plus 265. Okay, so how would you write out your answer correctly? You would do something like this. Let me just try and see what I can do here. If you want to write out your workings, you probably would write this one first. your delta W is pressure times change in volume. Then after that, you explain whether it's positive or negative. You say that because the gas is expanded at constant pressure, or you can just say volume increases. Volume is increasing. That means work is done by gas, so it's negative work. And then the third thing that you will write is this one. Delta U is Q plus W, so you sum in the value of your heat supply. This one is positive 442. This one is negative 176.8. Eventually, you get the final answer as 265 joules. Okay. So this one should be okay. Okay, then if you move on to the next part of your question, I'll just erase everything. Now, during the change from B to C, the internal energy of the gas decreases by 313 joules. By considering the molecular energy, state and explain qualitatively the change, if any, in the temperature of the gas. So if your internal energy is decreasing, what do you think would happen to your temperature? So this one, you can again derive it from the very first definition of internal energy, where we tell you that internal energy is KE plus PE. Change in internal energy is change in KE plus change in PE. Because your ideal gas has no intermolecular force, thus change in PE is 0. So change in internal energy is just change in KE. Okay, and then after that, mean kinetic energy is 3 over 2 KT. Mean kinetic energy is proportional to T, such that change in KE now is proportional to change in temperature. Okay, so if you then read your answer, you kind of need to explain it in this way. For an ideal gas, you have no intermolecular potential. You have no molecular potential energy because intermolecular forces are assumed negligible. This is first point. Your internal energy decreases, so total kinetic energy decreases. This is your second point. And the last point is because your mean kinetic energy decreases, your temperature decreases. This is your last point. Okay. So these are the points that are given marks here. But you notice that as you read it from one statement to another, it seems to be missing certain gaps in between, right? For example, like this part here, they didn't tell you that internal energy is equals to K plus PE. They straight away just say, oh, for ideal gas, there's no molecular PE. And then suddenly they somehow jump to internal energy. They did not explain to you that internal energy is actually your KE only. That would in turn explain to you why when internal energy decrease, your K would decrease. And then after that, the next statement also just say, oh, when mean KE decrease, temperature decrease. They also kind of didn't explain to you that mean kinetic energy is proportional to temperature. So you see, there's actually some missing gaps on information there. So usually when you read your answers for the specific exam question, it seems to be that there are certain gaps they're missing. It doesn't seem to tell you certain things. So that's why here you will notice that whenever I try to explain questions like this, I tend to write everything step by step. Because once you write everything step by step like this, it makes more sense. Okay? Just reading the answers by itself, somehow you will get the feeling that there are missing gaps in between. It doesn't explain how one sentence relates to the other. Okay, so just bear this in mind. All right, then after that, I'll move on to part 3. Now in part 3, for the change from C to A, use the data from B1 and B2 to calculate the change in internal energy. So what you had previously was a graph that looks like this, where you say that you have A to B, B to C, and then C to A, like this. So this one was A, B, C back to A. So they want you to use data in B1 and B2, the previous two questions, to calculate the change in internal energy here. The change in internal energy specifically from C to A. So this one, what you did know from the last two questions was actually the changes in internal energy. What they meant in part B1, you found out that the change in internal energy from A to B was actually plus 265 joules. Whereas the change in internal energy from B to C was negative 133 joules. This one was from B2, this part here. Okay, not 133, this is 313. And this one is negative 313 joules. Negative because it's a decrease. All right. So here, they want you to find out what is the change in internal energy from C to A. Okay. So this one, you make use of what you've learned just now. Because we know that internal energy is proportional to temperature. Change in internal energy is proportional to change in temperature. This one was a derivation that we did earlier. If your temperature change is 0, your change in internal energy is 0. Isn't it? When you're talking about something having gone through one full complete cycle like this. So here, you make use of that information. For closed loop, total change in internal energy is 0. So your internal energy change for your whole cycle, this one, your internal energy change for your whole cycle, which consists of UAB plus UBC plus UCA must be equals to 0. But you know the rest of the values here. UAB is plus 265. UBC is negative 313. You can subsequently find out what is UCA. Okay, so you sub in the relevant values, 265 minus 313 plus UCA equals to 0. Eventually, you find out the internal energy change as 48 joules. It is an increase. It's a positive. Okay. So that one is how you do this particular question. So for part 4, they mentioned that the temperature of the gas at point A is 227 degrees centigrade. Calculate the number of molecules in the fixed mass of gas. So you're considering point A now. You just use again PV equals to nRT. P is 5.2 times 10 power 5. V is 1.6 times 10 power minus 4. You can read the value from the graph. N is what you want to find. Molar gas constant is 8.31. And then your temperature is 227 plus 273.15. Okay, now your temperature here, this one is in degrees centigrade. When you want to change temperature from degrees centigrade to Kelvin, you generally either plus 273 or plus 273.15. Your marking scheme would tend to use plus 273. Your syllabus booklet would tend to use 273.15. But regardless of which one you use, both are acceptable. Okay. So like in this working here, while I may put it as 273.15, you could have just used 273 itself. It's actually easier for a lot of people. So eventually your N, the number of moles is 0.02, but the question wants you to find the number of molecules. So if you took chemistry before this, or you've gone through ideal gas with your teacher in school before, number of moles is number of molecules divided by your Avogadro constant. This is an equation that you will learn at some point. So you want to find number of molecules is this capital N here. Okay, so sub in everything that you know, you will eventually get the answer as 1.21 times 10 power 22 as your number of molecules. Okay.